Okay, I think we are live. Hello, Ryan. Thanks for coming. Thanks for joining us.
Thanks for having me.
I'm pretty excited about this. We've never done this before, but I think it's going to be cool. Yeah, I think I'll be a smarter person at the end of the conversation.
We'll see.
So, Professor O'Donnell, Ryan O'Donnell.
Yes, you may call me. Oh, please, go ahead.
You're a professor in the computer science department at CMU, and your field of research is theoretical computer science. You work on various different things within the field. I guess complexity theory is generally a good net to capture what you do. But recently you've been working or focusing more on quantum computation, I guess. Is that fair to say?
Yep, that's fair to say. True.
Yeah, and in fact, I'm going to say this. You are basically within the School of Computer Science. You are, I believe, correct me if I'm wrong, the only person actually doing research in quantum computation.
Well,
is that correct?
There's my students.
Well,
including
yes.
some undergrads.
I guess
They're doing some research in quantum.
I guess as a faculty.
There are some people, like one faculty in natural languages, I think, and one faculty in like the Software Engineering Institute, and one faculty at the business school, who all work on quantum, at least partly.
Yeah.
But yeah, I guess I'm the main person working on
it. Which begs the question, why is that the case? Because, I mean, if you think about what computation is or what computation is supposed to represent, like the the computational capacity of our universe is really captured accurately by quantum computers, not really by classical computers. If efficient computation is like what I call like faithfully capturing the computational capacity of our universe. So I cannot think of like a more fundamental topic to study when you're studying computation. Like quantum computation is really capturing what we can do in our universe as far as we know right now. So that's why it begs the question, how come we don't have anyone else?
Well, I guess one thing is we don't have quantum computers right now. So, it's not like so much of a chance for people to experience this, practically speaking, this quantum computing device. I guess I got quite into quantum computing about 6 years ago. I mean, seriously, for research. And I guess at that time, quantum wasn't as hot in the sense that, if you asked experts or me, to the extent I knew it, when are we going to have quantum computers really built and able to use? At that time, it felt like maybe I don't know, maybe 50 years. So it's a lot of people considered it highly speculative area. But then somehow over the last 5 years, I mean, the people working on engineering have gotten a lot better at it, trying to build quantum computers. And somehow there's been a lot of excitement, and now it kind of seems maybe we'll have them in 5, 10, 15 years. And yeah, so I think the excitement in the area has gone up, but then there's a pipeline problem. Maybe it encourages people to start thinking about it now, or maybe it encourages undergrads, grad students to start thinking about it now. It takes them a while to be,
yeah, I definitely agree. But I guess one thing that is interesting is that we're waiting for the actual computers to build the actual computers, where still it's very much interesting and very much fundamental to study it for its own sake and understand. I don't know, you probably know, computational ideas are going into understanding the fundamental laws of physics in the work of trying to combine quantum physics together with quantum gravity. There are computational ideas coming in there. People are looking at, entropy and how quantum circuit complexity might be actually relevant in some cases. And just, from that perspective, I feel it might very well be the case that when we do get a theory of quantum gravity, that computation might have interesting to say about, or have interesting contributions there.
Yeah, it could be. I'm not an expert on that, but actually all the things you said there were about kind of using the lens of quantum computers and computation to study physics. So maybe it's more interesting to ask, how come there are more physicists, studying quantum computation, which maybe there are. For the reverse, though, trying to import the physics ideas into doing computation better, I guess there's a question of to what extent is there really going to be a killer app for quantum computation? Will it totally change the way we compute everything, the way we do everything, or maybe it'll be more like supercomputers, which is a topic that's not that hot. They exist. People use supercomputers to do some specialized applications really fast. But, nobody's oh, let's study the theory of supercomputers. Well, some people are, but maybe it's yet to be determined which one it'll be more like.
Okay. So, we've been talking about quantum computation at a high level now, but maybe for those, of the people watching who don't know really what quantum computation is, first of all, how would you describe the concept to, let's say, some random person on the street who doesn't have any technical background? And then I'll ask you, how would you describe it to, let's say, an undergraduate student in a technical major, so might have some mathematical background?
Yeah, so I won't address maybe exactly how quantum computers work yet, but rather what they could be good for. Yeah, there is this like video series that you sometimes see on YouTube where like it's like one expert explains like a certain topic at like 5 different levels to like a child and like a high school student and so forth.
Yeah.
In fact, there's one on quantum computing, which is
yeah?
it's okay, yeah. I mean, it's a person from IBM. It's pretty nice. But like, yeah, when I teach my class on it, I usually, like do a version of that at the beginning of the class where I try to answer exactly that question. So I can tell you what I say there. So like, and I also compare it to like my own kid's age. So I'm like, okay, if I were to explain it to a kid who's 7 years old, I would say like quantum computers are good at finding patterns in data. Well, you wouldn't say data to a 7-year-old. So let's say lists of numbers. They're good at finding patterns in lists of numbers. And then for the 11-year-old, I might modify it a little bit and say they're good at finding clues about patterns in really, really long lists of data, like really long. Okay, and then if you get up to like the level of like a high school or something, one thing that you should emphasize is that like these like really long lists of numbers that quantum computers are good at finding patterns in, these are like really, really long. Like you should imagine like more numbers in your list of data than like there are atoms in the universe, like 10 to the 100, numbers, like you got a database that size. And an important thing to ask is like, how can like, if you have like, I mean, how can you give 10 to the 100, numbers, like a Google numbers to a computer? You can't write them down because it would take you too much space. But there's a way you can implicitly make a list of that many numbers, 10 to the 100 numbers. You can just write like a computer program. Let's call it P, a computer program that takes as input an index, which is maybe a 100-digit number, and it outputs a data point. And so in some sense, that computer program implicitly represents 10 to the power of 100 different data points, because you can give it 10 to the 100 different indices, like a 100-digit number input, and it spits out a data point. So you can have like a computer program that represents an enormous amount of data, like 10 to the 100 different pieces of numerical data. And quantum computers somehow are good at finding clues about patterns in this kind of implicitly represented data. So
that is amazing that in some sense you're saying like the universe has this enormous like hidden resource that you can poke into. Because like we cannot represent 10 to the 100. I mean, I cannot give something that big to a classical. I mean, the universe is not that big, but somehow implicitly there is access to this kind of secret resource.
Yeah. So like, the basic, unit of information in a quantum computer is this thing called a qubit, which is, let's say, like a particle that can have one of two different basic states. Like the easiest example I understand is like if you have a photon. It's like a particle of light. It has this thing polarization, which can be either vertical or horizontal. And like you even like interact with this in your daily life. If you wear like polarizing sunglasses, like they have these filters that only let in the photons that are like horizontally polarized, let's say. And so, they block out half the light. Perfect. Or like if you go to the 3D movies, you get like one lens that has like the vertical polarizing filter and one with the horizontal polarizing filter. So you can only see the vertical polarized photons with this eye and the horizontal with this eye. And so they just project two different images with like horizontal and vertical photons. And so you can see two images at the same time to get the 3D effect. So like one photon can have two different polarizations. And so if you have 100 photons together, which is no big deal. I mean, there's lots of photons in this world. The number of different polarizations they can have is like 2 to the power of 100. And somehow the true state of 100 photons is defined by 2 to the 100 numbers called amplitudes. You can think of them as like your data numbers, positive and negative numbers. And as you say, like the point is that like if you get 100 photons together and you have like a program that like implicitly represents 2 to the 100 different data points, you can like take this program and turn it into like an obstacle course for photons with like lasers and mirrors and things, such that when you fire the like 100 photons through this obstacle course of gadgets, when they come out, their quantum state is given by that list of 2 to the 100 numbers that your program has. And as you say, like, it's kind of crazy that like nature somehow has this magical power to like store like 2 to the 100 data numbers using just like 100 physical photons. And like this quantum computer scientist, Umesh Vazirani, has like a quote I like about this. By changing the photons physically, you can change their state, which means changing this list of 2 to the 100 numbers in certain ways. And he describes it as like hacking into nature's computer. So like there's certain things you can do to like, manipulate this giant data set using the laws of nature. And quantum computation is like trying to like, hack into the nature's computer to like manipulate these in ways that you like.
So let's maybe it would be nice to make a comparison between classical randomized computation and quantum computation a little bit. So just like going off the example that you gave with 100 photons, suppose that I toss a coin 100 times. So then I create a sequence, a random sequence of 100 bits. So each possibility, the state, you can say the state of this now can be represented by, you have all these different 2 to the 100 possibilities, and each one has a corresponding probability, which, maybe uniform distribution. So what is the fundamental difference between these two things?
Yeah, good question. So the difference is that like when you talk about the probabilistic state of like, let's say 100 coins, what you can imagine is like, imagine like you flip the coins and maybe they're like, I don't know, not even fair coins. They come up with different probabilities and so forth. But like you flip them like under like a cover, so I can't see them.
Right.
And then from my point of view, like I would ascribe to your situation, like the state of those coins, like a probability distribution, which is like one probability for each of the 2 to the 100 coin flip outcomes. And so in some sense, like, that's using 2 to the 100 numbers. But like these numbers kind of reflect, they're just like a mathematical reflection of my lack of knowledge of the true state of the states of the coins. So it's like these numbers like model, like, as I say, my lack of knowledge of the true states of the coins. Whereas, you can see the coins, they actually have some definite state. Like there's like 100 bits, there's no like mystery about it. But the weird thing in quantum mechanics is that, you can manipulate 100 photons in such a way that their state is truly defined by like 2 to the 100 numbers called amplitudes. And it doesn't reflect our like lack of knowledge about them or anything. It's like that's literally the the correct way to describe them. Just like when you have like a ball in classical physics moving in space, it's described by 3 numbers like the x, y, and z position. If you have 100 photons, their true state is described by 2 to the 100 numbers, and it's not. Yeah.
So like with randomize, you can just keep track of one sample, whereas with the quantum, you're in some sense, nature is just keeping track of the whole state for you.
Yeah, like when you run, let's say you like write a computer program with like some RNG in it, so like it has its own random coins. If you want to like mathematically analyze, such a thing, you'll have to consider many, the probabilities of many different things, maybe 2 to the 100 different possibilities if you flip a coin 100 times. But when you actually run the code, like there's just one outcome in reality.
But now there is an important detail though, right? So let's assume, what if like quantum physics was such that when you're looking at the superposition, these coefficients, that these amplitudes, let's say they turn out to be always like positive. Do we get any computational advantage if that was the model that we're working with? So somehow negative amplitudes is very much key, right? For the power of computation that quantum.
There's 2 things that are kind of key. It's true that so these amplitudes are kind of analogous to probabilities, except as you say that they can be positive or negative. as they always say, in fact, they can be complex numbers, but never mind. It's enough that they can be positive and negative.
Right. So like in maybe just a small note there is that, in quantum physics, the model uses complex numbers as the amplitudes. But if you want to do quantum computation, it's sufficient to just look at amplitudes that are real numbers.
Yeah, kind of in the same way, like if you want to like build a circuit, it's enough to use and or not gates. If you want to do quantum computation, it's enough to worry about positive and negative amplitudes and not complex ones. So yeah, this plays an important role. But another mathematical aspect that plays an important role, and maybe even more important, well, they're both important, is that, so you might ask, like, okay, if I get these 100 photons into some crazy state that's encapsulated by 2 to the 100 numbers, like, I want to get some information out. I don't just want to like put them into like a state. I want to like learn something. And you learn something by measuring the photons with a physical device. And in quantum, the probability with which you see a certain one of the 100-bit outcomes is proportional to the square of the amplitude. Which is kind of necessary that it's the square, because these amplitudes, as we said, could be positive or negative, but probabilities are always positive. So to have that make sense, you need it that like, the probability of seeing a certain 100-bit outcome is proportional to the square of the amplitude. And somehow this square is like, equally mysterious and like delightful and useful in quantum computation. If you've ever heard of Grover's algorithm, which is this like quantum algorithm for like finding an item out of a huge list, you can do it, in time, which is like square root the number of items you're searching through. And somehow that square root is really directly tied to this like fact that the amplitudes get squared when you measure them.
Interesting.
So it's a combination of those two things.
Interesting. Okay, so maybe let us get into some of the details about like what kind of quantum algorithms do we know about? What can we hope in the future? What kind of progress do we have and we can hope to have? So I guess when we talk about advantage in terms of quantum computation, maybe let's divide it into two categories. Like one would be like big advantage. Like, so let's say there's some problem that we don't know how to solve classically in polynomial time efficiently, but we can come up with a quantum algorithm that will solve it efficiently for us. So that will give us an exponential speed up. So in that realm, what do we know?
Right. There's a third category, by the way, but you can ask me about that one after we discuss these two. Right. So I always have a little bit of trouble when I like talk to people about quantum computation, because on one hand I'm like, it's so awesome, like it's the greatest thing, like it's so fun and cool, but I'm at the same time I'm like kind of like people ask me, so yeah, what can you do with quantum computers? And I'm like a little bit come off as pessimistic, like, well, only one or two cool things, but one cool thing is factoring integers. So as you may know, this task, I give you like a 1,000 digit number, find its prime factors. This is a really challenging problem. If you could solve that problem, you would there's like $200,000 prizes for solving such things. And if you could do it, well, the reason is it's the hardness of this problem is the basis for a lot of cryptography. So a lot of cryptography is based on the fact that this problem takes a super long time to solve with classical computers. But famously, Peter Shor around like 1994, 1995 showed that if you could build a quantum computer, it could solve this problem super efficiently, and therefore crack most of the cryptography that is in use now, definitely almost all the cryptography that was in use at the time. So that made a lot of people take notice about the power of quantum computers, potential power of it. So that's like one problem that quantum computers...
Because we don't know of a classical algorithm, efficient algorithm, but it's not like we prove that there's no efficient classical algorithm.
It's true. So, spoken like a true theorist. Yeah. So de facto, nobody knows like an efficient way to, any way to like factorize like let's say 2,000 digit numbers, and many people believe that there's no such efficient way. But as you say, we haven't proven it.
Yeah, I just want to make the point that it's not like this is not an example that proves that quantum computers are more powerful.
That is true.
Yeah.
De facto, though, I mean, like, we don't know any algorithm for doing factoring efficiently, but like, if you could build a quantum computer, we provably could, factor
True.
these numbers super efficiently. So people are all psyched about that, and they're like, oh, let's find some more problems like this, and nothing. Sorry. I mean, there are a few like other...
there's discrete log, I guess.
Yes, there's like some related like number theoretic kind of arithmetic thing related to cryptography. And, the true believers will be like, oh, there's some other thing like Pell's equation. I mean, not to...
But there, I guess, like one response to that would be, okay, so we don't believe that quantum computers can solve NP-hard problems efficiently, right? So we don't believe that NP-hard problems have enough structure that quantum computers could exploit. And so now if we're talking about, okay, like exponential advantage that quantum computers will give us, we are looking at problems that are not NP-hard, but also not NP. So what we would call like NP intermediate problems. But what do we have in that space? Like, it's not like a very rich space of like very lots and lots of problems, is it?
I mean, depends how you look at it. I mean, traditionally you would say like, oh yeah, there's factoring and there's like graph isomorphism.
Right.
Like with graph isomorphism, this is the problem of, given like two graphs, are they really the same graph if you just like renumber the vertices? That's a funny story in the sense that for a long time, like the most efficient algorithm we knew for graph isomorphism was exponential time. But somehow it was de facto easy in the sense that like nobody could come up with like a way of producing tricky inputs, like two graphs that like seemed isomorphic even though they're not, or vice versa. And like, all the heuristic algorithms we had like solved the problem great in like polynomial time. So people kind of believe that like maybe there is a polynomial time algorithm for graph isomorphism. And after Shor's algorithm came on the scene and like solved this NP intermediate problem factoring, people are like, oh, definitely graph isomorphism is the next. And there's actually good reasons to believe, based on like the kind of patterns that quantum computers are able to get clues about, that you could maybe do solve graph isomorphism efficiently. And so people got pretty excited, but then like they couldn't make it work. And even they started proving theorems about like why their algorithms that you might try couldn't work. And then they mostly stopped thinking about it. And then like in the meantime, like, Latsi Babai, a famous computer scientist, gave like a pretty efficient algorithm for graph isomorphism. He didn't show that it's in polynomial time, but came very close. So that was funny, where like classically algorithms leapfrogged over the quantum.
I mean, I guess it's fair to say that most experts believe that it would be solvable in polynomial time.
Apparently, Latsi Babai believes that it's not in polynomial time.
Oh, wow.
It requires n to the log n time.
That's very
And
interesting.
It has some reasonable reasons. It's related to the group isomorphism problem, where it's like natural to suspect that n to the log n could be the right running time. But I don't know.
Okay, so we have, I guess graph isomorphism is a good candidate, but then is there any other like natural candidates that we might want to think about?
Well, right. So there are, interestingly enough, it has something to do with, this whole question has something to do with cryptography, it seems. Because, once it was shown that quantum computers, if built, could crack all these cryptographic schemes that are used all the time based on factoring numbers. Like whenever you type HTTPS into your browser, it's using a cryptographic scheme that assumes that factoring numbers is hard. Once people discovered this, they're like, uh-oh, we better get some like new kinds of cryptography,
right?
That quantum computers maybe can't crack. And interestingly enough, there's already developing this like kind of parallel line of work, had nothing to do with quantum, about trying to get like new styles of cryptography based not on factoring integers being hard, but by problems about lattices being hard. So lattices are like the geometric concept that you might have heard of, like, these like regular repeating points in space. And people found that like you could actually do some interesting and cool cryptography if you assume that certain problems about lattices were hard. Like I gave you like a lattice in one format, but you tried to find like two close points in the lattice. These problems also seem to be not obviously solvable in polynomial time, not NP-complete, and maybe useful for cryptography. And so this was like another area where like people got excited in the quantum field, like maybe quantum computers can solve these lattice problems. And again, kind of made sense because like, again, like something about, there's like, periodic structure in a lattice. It's kind of the kind of thing that quantum computers could be good at. So people have tried cracking those problems with quantum computers. Hasn't panned out. I've heard about two famous people recently who claimed they had a efficient quantum algorithm for solving these lattice problems.
Ooh.
But before they really went public, they circulated around like other people to check, and in both cases it didn't work. But who knows? Maybe the third time will be the charm.
Yeah. Oh, that's exciting. So okay, so we have some problems there to work on. If you're a quantum computation scientist, you may want to work on those. So maybe let's move on to the second category, which would be for those problems we do know how to solve, let's say, efficiently in polynomial time classically. Are there quantum algorithms that provide, speed up over what we know? Maybe it takes from n cubed to n squared time, maybe some kind of a quadratic speed up.
Yeah. So after Shor's algorithm came out in like 94, 95, pretty soon thereafter, there was like the second famous quantum algorithm came out in 1995 or 96-ish by Love Grover. And this is an algorithm for like a very simple problem. Like imagine you have an array of bits, and you just want to find one position in the array where there's a 1. Or, you want to believe that there are no ones in the array.
So like in 251, we like to call this the battleship problem.
That's right. It's also a great problem for discussing randomized computation because, a deterministic algorithm, what can you do pretty much other than check the first position, check the second position? Like it's not sorted or anything. There's no pattern. So like just go through all, let's say if it's length n and positions to try to find a 1. With the randomized algorithm, maybe you can do like a little bit better depending on how you look at it. I mean, you might try picking positions randomly to see if there's a 1 in that spot in the array. But it'll still take you, a number of tries that's proportional to the length of the array. But Grover's algorithm, if you have a quantum computer, you can solve this problem with high probability using about square root of n, accesses to the array. So as you say, this is like a speed up from n down to square root n, but not an exponential speed up.
Right.
But still pretty cool. And you can use it for a bunch of things. Like, you can generalize it, for things like, find the minimum value in a list of numbers, also in square root n time, in a non-sorted list, or other kind of like, search and optimization problems. So there's a lot of maybe basic problems where you can get an algorithm that's like square root as fast if you have a quantum computer. And for me, actually, as like a complexity theorist, my favorite such problem is circuit SAT. So if you think about the circuit SAT problem, that's the problem where like you're given a circuit diagram. And you want to know, let's say with n input wires and 1 output wire, and you want to know, or you want to find, let's say, some setting of the input wires, the n input wires, that makes the output wire output 1. That's circuit SAT. This is like the most classic NP-complete problem. And basically the best algorithm we know, like on a normal computer, randomized or not, takes time like 2 to the n. There's not much you can do other than just like try all the 2 to the n inputs and see if any of them make a 1. You can think of the circuit as like, I was talking at the very beginning about like an implicit way to represent a huge amount of data. This circuit is like an implicit way to represent 2 to the n bits. The 2 to the n output bits you would get as you varied over all 2 to the n input strings. And the circuit SAT problem is really like find like one of these, right, positions where you get a 1 in the output.
Right.
And so a quantum computer can solve that in time square root of 2 to the n, which is
2 to the n over 2.
That's right, which is like square root of 2 to to the n. So it's like 1.4 to the n. So it solves this NP hard problem, NP complete problem, circuit sat. Instead of in 2 to the n time, it solves it in 1.4 to the n time, which on one hand, it's still exponential time. On the other hand, it's like way faster. And there's a strengthening of the P versus NP assumption called SETH, strong exponential time hypothesis, which is quite popular these days in complexity theory and algorithms to study. And it's the hypothesis that like for a circuit sat, any algorithm will take 2 to the n time. So if you have a quantum computer, it actually breaks that stronger version of that P versus NP hypothesis, SETH.
So for problems that we know how to solve in polynomial time, are there instances of where Grover is used to speed up what we classically know?
There could be, yes. There could be, yes. A related kind of phenomenon that you can get out of Grover is if you have like a randomized algorithm that maybe is trying to solve a problem and it finds you the answer with probability epsilon, or like, let's say 1%, then, you have to try it like about 100 times before you find your answer. But with Grover, you can sort of automatically get the square root of that. So you'd only have to try it around 10 times to get the answer. So for like speeding up algorithms based on like random algorithms that have a failure probability.
I see.
This is an example.
Good. Yeah, that's nice. So you said like there's a third category. So what's that third category?
Right. So people are always like disappointed because, I sometimes say like, well, there's Shor's algorithm for factoring, there's Grover's algorithm for search. Like that's kind of the two, traditional problems we know where quantum computers would give like a big speed up. So there's not clearly so many amazing applications of quantum computers solving classical problems. But the third category is quantum computers solving quantum problems. And this is actually kind of what interests me the most in research.
So
what's
a quantum problem?
Right.
Yeah.
What do you mean by quantum problems? Well, like, understanding, like, analyzing quantum systems, like understanding, like if you have, the quantum analog of a SAT problem, you have like some quantum apparatus that takes in particles and, messes around with their quantum state and then outputs 0 and 1, how would you, what's the fastest algorithm for analyzing that? Or like algorithms, maybe you're getting some like quantum data and you want to like analyze your quantum data, or you want to like, analyze or model like, molecular interactions and so forth. So these are all like quantum problems, and like in some sense people like, most computer scientists like don't deal with them. They're like, I only have classical problems. I have like a regular computer. I'm trying to solve.
So this is like the original motivation behind quantum computation as well, right? So like to be able to simulate quantum systems efficiently.
Exactly. So I mean, you pretty much, well, you don't have to, but you pretty much have to have quantum computers to like do it efficiently. And that's what I think is like maybe the most exciting thing to work on theoretically and also in practice. So as you say, I mean, in some ways this was like the origin story of quantum computing. A couple of people, like including like Richard Feynman and somebody in the Soviet Union whose name escapes me, Manin maybe, had the following like brilliant observation. They realized that the rules of quantum mechanics involve like these like exponentially large number of numbers, that like when you manipulate 100 photons, the rules for how the manipulations work involve manipulating 2 to the power of 100 numbers. And they're like, boy, it's like completely impossible for our normal computers to, do these calculations, or it would take them like an exponentially large amount of time. But you have this physical system that's doing these manipulations, namely the particles themselves. So if you just regard the particles as a computer, then they're simulating themselves and doing the perfect job of it. So getting kind of back to that Umesh Vazirani idea like of hacking into nature's computer, the idea is that like, okay, if we can just use these particles to, compute things, we could have like some exponential speedups. But it seems that the things that they might be best at are for computing and analyzing and manipulating inherently quantum situations, as opposed to trying to shoehorn our classical problems like factoring or Hamiltonian path or whatever into a quantum computer.
But still, it's not like, quantum computation is this giant, massive parallel computation. As we talked about, we don't think that, you can just solve NP-hard problems. I guess, if people are wondering, wow, that sounds amazing. Why aren't they more powerful than you might think? Why can't they solve NP-hard problems? What's a good answer to that? Is that related to measurement?
Two things. One is that as we kind of mentioned before, you can kind of get an enormous amount of data into a tiny physical system. If you have a program that takes 100 bits as an input and outputs a number or an answer, you can convert it into some physical, obstacle course for electrons or photons or whatever that will kind of encode all the 2 to the 100 answers into the state. But you can't get them out so easily. So as I mentioned before, the rule for how you get information out is you measure the photons, put them into some kind of detectors, and basically you get back some 100-bit string with probability proportional to the square of the amplitude. So you kind of get a sampling from the important answers or the large values, which may be useful or it may not, but it's not like you can just pick your favorite one of the 2 to the 100 answers and find out what. Well, you can actually do that, but you can't. There's only a small number of things you can do with these answers. So how to get a useful answer out of this quantum state is part of the challenge. And the other part of the challenge is, as I kind of alluded to before, what quantum computers are good at is finding certain kinds of patterns in data. And these are patterns related to Fourier transforms. And so, that's what they're good at, but it only works if you have data that has a very special pattern in it. A quantum computer maybe is good at picking out what that pattern is. But if you have just a big mass of data with no particularly special pattern in it, then there's not necessarily any good reason to believe that a quantum computer can help you extract anything out of that data.
So when you say quantum computers are great at finding patterns in data, you're referring to quantum Fourier transform?
Yeah, exactly.
And is that the one trick that quantum computers know how to do? Can we boil down the power of quantum computation to this one thing?
Yes.
Oh, wow.
I was actually, I didn't know this, and it wasn't really explicitly written down until 5 years ago or so.
It's going to be you now. I'm gone.
Uh-oh.
That's okay.
Okay. But in some sense, this quantum Fourier transform is the one trick of quantum computers. So let me say a little bit about it. I'm not an expert on physics or anything, but there's something that maybe you've heard of the Fourier transform. It's about decomposing signals or data into frequencies. So if you mash your hands on a piano, it makes some chord sound, and that's really just some weird pattern of how the air fluctuates or vibrates over time. And this fluctuation is a combination of the different frequencies. If you hit A, it's a pure 440 signal, 440 beats per minute. If you hit a different note, it's some different number of beats per minute. And the whole chord or sound is some combination of intensities, of volumes, and frequencies, how fast you press them. And so Fourier transform takes just a full sound and transforms it into these frequencies and intensities. If you hear a giant sound, the Fourier transform tells you it's exactly this volume of this note and this volume of that note and this volume of that note. And this is what the quantum computer can do. If you have an enormous data set that you think of as, analogous to like a sound, then the quantum computer can exactly kind of find the large frequencies in the data, or these large repeating patterns in the data, and give you a sample from like the most important frequencies. So that's like the main trick, this efficient Fourier transform on giant amount of data that quantum computers can do. And you can even prove a theorem that says that like kind of without loss of generality, any quantum computer program can be thought of as like alternations between doing the quantum Fourier transform and doing some normal classical computing, and then doing quantum Fourier transform and some normal classical computing. And yeah, when I learned that, it made me very happy because it like puts a lot of the algorithms into like a common framework. And also, I happen to really love Fourier transforms.
Yeah.
And so I was like, oh, this is great. Like, it's exactly speaking my language. I can use, if there's somebody that like knows lots about Fourier transforms, but like nothing about, I don't know, quantum, you can explain it, the whole story, in terms of only Fourier transforms.
Okay, actually, that prompts me to ask this question of like how you got into quantum computation, because it's not that, you know, your graduate school work is not on quantum. You got into this field. How many years has it been now?
About 6 years.
6 years.
So
what attracted you to the field? What made you say like, okay, you know, this is something that I can really see myself get into?
Yeah, so there's two components to this story. So, you know, when I started, you know, as a graduate student, like working on theoretical computer science, you know, you hear about all sorts of different topics, and one of them was quantum computing. And, you know, it seemed cool to me, but I, like many other people, was kind of like skeptical. I was like thinking, wow, there's a very fanciful like notion of computation. Maybe these quantum computers will never be built. Like, it seems like odd to spend a lot of effort studying them.
Okay.
And I clearly remember like I was like hanging out with this other person who's also a computer science researcher, Scott Aronson, who has like famous on the internet for like blogs and so forth, has always worked on quantum computation. You know, I was still feeling skeptical, and I kind of like, you know, teasing him a little. I was like, you know, what is this quantum you're working on? It like you're pouring all this time into it. Like, you know, what if it like doesn't pan out? And he gave like such a great answer that it really stuck with me. And he gives it all the time. He's like, you know, if it doesn't pan out, that would be even greater than if it does pan out. He said, you know, if it pans out, then that's great. We have quantum computing. If it doesn't pan out, quantum computing, it must be because, you know, we're completely wrong about the laws of nature being quantum mechanics. So if quantum computing is impossible, it means we must discover something super new about like the laws of physics. And like, that's amazing. Like,
or maybe not maybe completely wrong, but maybe incomplete, you might say. Like, you know, we had like Newtonian physics, and it was like, whoa, really good, really good. And it's still good. It's still great. Like, you know, Newtonian physics, we can still like send people to the moon with classical physics. But then when you look at like, you know, high velocity situations or like high energy situations or very tiny particles, you see that, oh, it's not actually doing a good job with those things. And maybe, I guess like the current, you know, skeptics of quantum computation, or like skeptics of that, you know, people that say like quantum computers will never be built. Their point, I guess, is that at that scale, when you're talking about thousands of qubits and all that entanglement, that can be like perhaps analogous to like the high velocity, high energy regimes in classical computation, so that we might have to actually augment what we know about quantum physics and come up with maybe that will lead to new discoveries, new laws of physics. And in that sense, yeah, it is very exciting. That would be even better.
Yeah, exactly. So it's like, it's literally win-win. I mean, it's even better if it doesn't succeed. And I was like, wow. I mean, that shut me up. Like, perfect answer. You're right. So, you know, I just went along in my life and continued to think it's cool, but, you know, and wasn't so skeptical, but I never really worked on it. But what got me started working on was literally one specific person, my graduate student, John Wright. So I had this graduate student, John Wright, and we had, you know, done some research on like different things. I used to work a lot on Fourier analysis of Boolean functions, and he worked on some of that too, and optimization algorithms. And I clearly remember like one day we had a meeting. I was sitting in my office. He comes into my office and he said, you just started the conversation by saying like, I never told you this before, but I'm really interested in quantum computing. And it's like, whoa, I never told you this before, but I'm also really interested in quantum computing. And we were like, okay, well, let's try to do it. So like we should work on it. It was really kind of all down to him in the sense that like, I was like, okay, find us a problem to work on. And he thought about it and he brought like some problem in quantum computing to work on. And we worked on it and it was super fun. I loved it. And that's really exactly what got me into it.
That's great. So that's like a nice story also about like how, as a graduate student, you can get your advisor really interested in something. And that's like...
yeah,
that is an option, I guess. Like, it's not like you always have to work on your advisor's topics necessarily.
Yeah, it's even better if you set your own direction. And
Yeah.
like now he, only works on quantum computing, and he proved some like super amazing result recently with some other people. And he's a professor of computer science. So
I know.
Happy story for him.
Yeah.
And me. I got me into quantum computing.
Now he's like maybe right next door to Scott Aronson.
That's right. He's at Austin with Scott.
So this brings another question to my mind, which is that you are working on quantum computation research, but you're not a physicist. You don't have any physics background, I think.
That's correct,
or
yes.
maybe like you haven't told me
No.
this time.
No.
So it is very interesting, maybe someone who doesn't know much about quantum computation, that you can be an expert in quantum computation without knowing any physics. Is that fair to say, first of all? And why how is that possible?
I think it's fair to say. I don't say it with like pride that I don't know much about physics. I say it with like some shame, but it's true. Like, I don't know a lot about physics. I'm trying to learn. Like other sciences too, like chemistry, I know like zero about it. Like I dropped out of chemistry in like 11th grade. But indeed, you can work on quantum computation and even quantum physics, oddly enough, without really knowing anything about it, just because, like the rules and the laws of quantum computation are math. And like, I kind of truly think of myself as like a math person, not even like necessarily a computer science person or physics person. And that's great. You can also work on theoretical computer science without being very good at programming or knowing anything about like operating systems, programming languages, or anything. You can work on theoretical computer science if you know some math, and then people tell you like some interesting problems to work on. And it's kind of similar for physics. So I don't really know what like the spin of an electron is, and I don't really know what like measurement means or how you physically do it. But the textbook just says, page 1, like, okay, here's like the 3 facts from math you need to know to start doing quantum.
Right.
And you can.
It's kind of like here are the axioms of probability. Then you can do probability, and here are the axioms of quantum mechanics, and then you can just start working on it without ever really knowing how that math maps to reality, I guess. And
yeah, I've learned a little bit about it since, but actually it's nice that you mentioned probability, because I really think about at least the part of quantum stuff that I work on as quantum probability is it's like a generalization of probability. So in some sense, quantum, kind of like you were saying before, like we have like the laws of probability that we use to model like rolling dice and coin flips and random things in nature. But when you get down to the level of like microscopic particles, according to the textbooks, the laws of probability are kind of different. There's like a generalization of them that includes like a good old regular coin tossing, coin flipping, and dice rolling probabilities. But like it involves something more general where like, I don't know, the probabilities get represented by like matrices and things. And that's actually the part of it that like I'm most interested in, like quantum information theory, quantum probability, and like quantum learning. So, learning theory and probability theory are really tied up together a lot, because you usually have like some probabilistic model of where your data that you're trying to learn is coming from. And so I'm really interested these days in like kind of the quantum version of that problem. Not trying to use quantum computers to solve classical learning problems, but trying to use quantum computers to solve quantum learning problems, or you have some quantum probabilistic system that you're getting data from and you want to analyze it or learn something about it.
Yeah. So And I guess I can also say that the math behind quantum physics is very elegant, actually. Like if you don't think about how it maps to reality, like you're happy. You're like, it's like, this is wonderful, nice geometric stuff. I can visualize things and...
Yeah, I mean, that was really what kept me going in quantum after this, I got started with John. Like the problem we picked was kind of lucky. Like it was like so beautiful mathematically as it turned out. Like I was like, wow, this is like so gorgeous. Like I'm just enjoying so much thinking about these like cool math problems. It's great. It's also like, there's a feeling like, do you ever play like some video game like Zelda, I think had this, or this game Minute, where like you beat the game and you're like, hey, I won the game. And then there's like, oh, there's second quest. And like second quest, you can like basically play the whole thing again. It's like a little bit different. Like the world seems the same, but like there's like differences and it's like a little bit harder. And you're like, oh, I thought it was done. I get to play the whole thing again. It's somehow exactly like that with like quantum probability and probability. Like, I spent like, 15 years like doing like math problems related to like probability, and that's cool. Did a lot of fun stuff. But then like the quantum version is like the second quest version. Like now take every problem you ever did and like it's like kind of cooler, harder, and like more exciting. And
you've
like,
completed that level, so it's now to the next level.
Yeah. So like I was like, oh, this is great. I have so many cool problems to think about now.
Yeah, it combines nicely Fourier analysis, probability, stuff that you're really interested in.
Yeah.
Do you do you get curious about how this math maps to reality? Do you like watch stuff online?
Yeah, I do. I'm trying to learn now, and like I don't know. I'm checking out a few things. I watched this like Sean Carroll series, like The Biggest Ideas in the Universe. Pretty good.
He's awesome. Like he's a very good teacher.
I'm about halfway through that. Trying to read this like book, like a textbook on the standard model of particles by Peter Voigt right now. One thing that's like kind of hard or funny is like I'm a weird audience person for this kind of thing because, okay, in some sense, like I'm kind of an idiot that doesn't know anything. Like, so I need like these really high level like overviews that like explain things from a very basic point of view, the physics. Except like I'm not an idiot about like math. Like I actually know like a lot of math. So I'm kind of like, oh, if there's only like a, somebody trying to explain things to a person that knows like tons of math, but like absolutely no physics, that's the thing for me. But of course, that's like a really weird combination, right?
Yeah,
it's
we
like
can't expect a popular book on that, I guess.
It's either like a book for people that know lots about everything or like nothing about anything. So.
Yeah, that's interesting. So what do you make of like... let's say the measurement problem and like, this like weird thing, like what's going on when you measure a qubit, let's say, and then there are like different interpretations of quantum physics and like, what's your favorite interpretation?
Yeah, let's see. So, I guess this refers to like some tension in like the theory of quantum mechanics that even the physicists can't resolve, where like, the laws of quantum computation are supposed to be like reversible, except that there's this like weird thing you can do, measurement, which is not reversible, and nobody can exactly say what it means, and so they need some like interpretation to explain it. I have like a few opinions on this. So like one is, there's one like philosophy where you're just like, well, whatever, like I don't care, like I guess I just know like what it means practically to measure some photons, and like I have a system for working out what will happen. And like, that's good enough for me. And I kind of am like that too. Like, I don't really know anything about physics. Somebody told me, here are the math rules. And I'm like, okay, fine. And I'm happy to just think about, what kind of cool quantum, algorithms we can build from that. To the extent I understand anything about this, like, measurement problem or like interpretations of quantum mechanics, there's one like this crazy sounding one, like the many worlds interpretation, which is that, whenever something quantum mechanical happens, like the universe like branches into like, if you have 100 particles, it's going to branch into the 100 copies that represent all the possibilities. This was espoused by this guy, Everett, and wasn't really taken seriously at the time when he wrote it in his PhD thesis, and then only later was it kind of brought back. And I like to talk about this guy in my class, and his like son's like a famous rock musician and so forth.
Nice.
But like this is the interpretation that like it seems crazy to physicists that you would have like all these universes, but it's definitely the interpretation that like makes the most mathematical sense. It's like super mathematically elegant. Like the rules are like quite obvious.
It doesn't add anything extra, right? Like, I mean, maybe just to compare it to something, let's take the classical like Copenhagen interpretation is like
what's more than me. Go ahead.
No, like the textbook. When you open a textbook, like you probably see the Copenhagen interpretation, which is like, if you just leave the system alone, it evolves according to these rules. But then when you measure, there is a different set of rules, and then when you first see that, it's like, oh, that's not elegant at all. That doesn't sound right at all. And what does it mean to measure? Like, if I just like, if I look at it, is it a measurement? If frog does it have, does it get measured? If I just like quickly look at it and turn my head, what happens? So there's all those kinds of stuffs. But like with many worlds interpretation, we don't have all that baggage, it seems, right? So it's just like, it's just one rule that we have, and then the measurement is explained using that rule, right? With entanglement, with the environment. Yeah, I don't to be honest, know 100% of the details, but I remember like talking about it with like my friend Guy Kindler, and he's like, he understood it better than me, and he was like, as a theoretical computer scientist, like this will definitely be the interpretation that you'll gravitate towards. Like it's the one that somehow like makes sense. I don't know, to a theoretical computer scientist. There's like another. This is a bit technical, but there's like another point of view that this is like betrays my like ignorance of the subject, which I never understood, which is, as you say, like there's these axioms where like everything is like time reversible, except that like there's something called measurement, which is like not reversible, and that seems like very upsetting to the physicists, and it causes them a problem. There's like a formalization of like the math laws of quantum systems where that involves like mixed states and quantum channels instead of unitary transformations. This is some technical talk, but in that mathematical framework, everything, measurement is one kind of operation, the unitaries are another kind of operation. Everything is like fine. It's like a very nice mathematical framework. It's not reversible. But I'm like, I don't know, is that a problem? And it always seemed to me that like this, I guess another problem with this is it really admits that like the state of particles are like randomized, that like it's not even that like they have all these amplitudes, but just even what the amplitudes are is like randomized, and somehow the physicists don't like that because it's like not deterministic in that way. I'm like, if you're already admitting randomness into the picture, like, why not have this as well? So I never understood why this was not like an acceptable interpretation, but I think that's mainly just my lack of physics knowledge. Yeah, it's fascinating. I mean, I guess it's fair, to say that, well, I don't know, but even like, as you said, physicists don't necessarily agree on what is the right interpretation. Do you know if like these different interpretations are in principle distinguishable? Like we can in principle have experiments that can distinguish between them? I think some of them. There's another one that also kind of caught my fancy. I forget the name of it. It's named after some Italian people, I think, with like a 3-letter acronym, where basically everything is like reversible and everything is like nice and fine and dandy, except just very, very occasionally particles like decohere. And this is what causes the measurement phenomenon. Like when you measure a photon, it's really going to some physical system where like the atoms of the detector get entangled with the photon, and the atoms in this part get entangled, and so you get like this larger and larger entanglement. But in this theory, like, just on a clock, like every particle has like some minuscule chance of decohering, which sort of snaps all the particles together into like one state. And so it's kind of like a statistical mechanics-y kind of interpretation. And some physicists don't like it because they're like, well, why should this happen? And like, why should, there just be like some probability that a particle decoheres, and like, what should the rate be? And I think like, I don't know, that seemed like a cool idea to me. But I think this is something that you can try to physically experiment on to
if this were true, then what would be the rate at which particles decohere and so forth.
Nice. So we've been using the word entanglement, I guess, a few times, and people might be wondering, what is this thing called entanglement? That's like a important buzzword, I guess, in the quantum world.
Yeah, entanglement is just refers to the fact that, just kind of to the fact that, like, if you have 100 photons together, their state is defined by 2 to the 100 numbers, as opposed to like just 100 numbers. Their state can be like fully mixed together, and like you can't explain it by saying, okay, tell me the state of the first particle, tell me the state of the second particle, tell me the state of the third particle. If you have like 100, balls like flying around in space, you can just say, okay, this ball's coordinates are XYZ, this one's are XYZ, and so you explain the position of 100 balls with 300 numbers, like 3 XYZ coordinates for each. But in quantum, like, it's not, 2 numbers per photon, so 200 numbers. It's like 2 to the 100 numbers, and like all of them together are defining the state.
So would a synonym be like non-separable?
Yeah, basically, yeah. It's very analogous to the notion of independence in probability. So like, if you flip 100 coins, but you do them like independently, like totally separately, and like, let's say they each have, probability P1 for the first one to come up heads, P2 for the second one to come up heads, P3 for the third one to come up heads. And like the probability that all 3 come up heads is like P1 times P2 times P3. And this reflects that, these are independent events. But you could have like some more crazy, like, I don't know, like gadget that like, didn't flip the coins separately, like it did some combined thing with them. And they could get into a state, a probabilistic state, defined by 8 numbers, the probabilities of heads, 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 tails, etc. That is not just defined by like, taking the products of a probability for this one, a probability for this one, a probability for that one. So this is like a good example of how, well, it's related to this like notion that like the laws of quantum are kind of like a generalization of the laws of probability. Right. And this entanglement is like a generalization of the concept of non-independence.
Correlation.
Yeah, exactly.
Yeah. Okay, so let me ask you one more thing about quantum.
All right.
Quantum teleportation. Let's talk about that.
Okay.
It sounds really cool. What is it?
Quantum teleportation. Yeah, it's a really cool name. Some people like came up with some great names. It's a really cool idea too, but I have to preface it by saying, as you may know, Noel, it doesn't involve teleporting matter. It sort of involves teleporting information. Even in that sense, it's like not so amazing because it involves, sending some classical information between 2 points,
right,
in order to
send
some quantum information. So it's something like the following. If you have like a qubit, a single like photon, its state is defined by 2 numbers that can be positive or negative, and basically you can think of it as like 2 real numbers between -1 and 1. But it has like arbitrarily many digits. It could be 0.3296 blah 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 blah, and that's like the state of the photon. And teleportation is like some like magic trick. Well, it's not magic. You can really do it. Where if like, let's say you're at your house and I'm at my house, and I have I found like a cool photon in my house. It was in like some funny state, and I don't even know what the state is yet, but it's got like some, it's defined by 2 numbers between -1 and 1. There's some magic trick I can do where like I can like, do something at my house, send you a text message that's 2 bits long. So 1 of 4 possibilities. I send you a text that's either 00, 01, 10, or 11. And then you do something at your house. And at the end of this story, you have a photon whose state is exactly the state of the photon was in my house. So like its state is exactly 0.389 blah 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 or whatever. And what's kind of crazy about it is we didn't physically, and actually I lose the photon, so like my photon is gone. So we didn't like move the photon from my house to your house. I mean, I could have done that, just got in my car and driven it over, but I was too lazy to do that. but it can be like, this state, this like, two, real numbers can be like teleported to your house.
Right.
Even though I only sent you like 2 bits, which
Exactly.
is not enough to like describe the whole state.
Right. I mean, the quantum qubit has many more bits of information in it, but somehow you were able to transfer that knowledge.
Yes. There's another catch too, which is that in order for this to work, we must have pre-shared 2 entangled photons.
Right.
So like you need this as like a catalyst to do this as well. So for this whole magic trick to work, like you have to have like a photon in the fridge, which is like entangled with a photon I have in my fridge.
Yeah.
And then if I find like a second photon, then I'm like, oh, this is a cool photon. I want to send its state over to a null.
Yeah.
Then through the combination of like destroying these 2 photons, the fridge one and the new one, plus this like 2-bit text message, you can get
get it on the other side. And this is experimentally verified.
Yeah, this is like one of the cool things that they definitely can do. Let's see, they can do this for a while. The first time when I started teaching a quantum course, like the cool thing was they could do it like at a distance of some 170 kilometers between like 2 islands in the like Tenerife and something like in the Canary Islands. They like did an experiment to do this teleportation. But since then, like this guy Zhengwen Pan in China and his group did it between a satellite in Tibet and a space station that was like, I don't know, 100 miles into space. So yeah, this is like one that they can literally do now.
So I guess there what you would want to do is you start with an atom, then a molecule, then maybe a tissue, and then eventually, let's say, we come to a point where, let's say, we have the technology to teleport a human being. Right, that would be great. So like I will be here and I want to go to Turkey, see my family. We have we have shared entanglement with Turkey.
A fridge full of,
and then I would hop onto
particles.
my teleportation machine and teleport myself. And well, I would disappear here and reappear in Turkey. So my question to you is, if we were to build this machine, would you use it? In the sense that, what's really happening? Are you like dying here and then
now we got real deep.
And then a copy of you appears on the other side, which looks and talks like Ryan, but not really you?
Let me stall for 1 second by like adding like a more prosaic comment, which is like, if you're like a science fiction writer about teleportation, then you have this like problem that like, oh, like if I can like make a copy of a null, then I could make 2 copies of a null. I could make 3 copies of a null.
Right.
And then, like the world would be full of like a nulls. That'd be crazy.
Yeah.
But actually the laws of quantum mechanics have this property called no cloning, which basically means if you're trying to like copy some object, you can make like exactly 1 copy of it and it sort of ruins the original copy. So at least this preserves the property, this fantastical property that there will only be 1 copy of hypothetical a null anywhere. But actually really that only, that only assumes you can't like exactly learn, the state of an object. I mean, you could think like, oh, I could like teleport this like candle by like exactly analyzing it, figuring out the state. I know every like detail about it, and then I'll just like build 5 copies over here, and like, oh, ta-da, I teleported it. But I guess one issue is that only works if like it's sort of like the classical state of the thing. If like the quantum state of this, candle is like truly important to its essence. Right. Then we cannot build a machine that makes copies of that. Just, as you say, kind of we can teleport it around. So then I guess part of the question is like, all right, this is again a physics thing I don't know. Like, is some part of my essence like tied up in the quantum state of the particles of my body? Or is it merely like their, classical arrangement? I don't know. I dropped out of 11th grade chemistry, so I don't know. But okay, let me engage with your question for real.
Would you use this machine?
Sure, and I'll tell you why.
Interesting.
I guess one insight that I kind of like from, I think even theoretical computer science, especially it came out of an insight from theoretical cryptography, is that like if 2 things seem indistinguishable to an observer, then you should just count them as the same. And so in that case...
Well, I mean, from our perspective, we would be happy. I mean, we still have Ryan in the world, and it's the same Ryan. But what happens what happens to you, I guess, from your perspective, it may not be the same.
If it's literally the same state, then it should be fine, right? I don't know.
Yeah, I mean, it goes to this question, it's a philosophical question, like what makes you you? Is it the is it the classical information enough? Is it like the quantum information? Or is it like your physical atoms in your body? Is that like what makes you you? But what's interesting, I find, is that, every 7-10 years, all the atoms in your body is replaced with new ones. So like you can say, well, maybe it's not then the atoms, but it's the information in the atoms. But yeah, and then this connection to the no cloning theorem, I've always found that very interesting, curious, because it's like, if it is really the quantum information that makes you you, and if there was no cloning theorem, like we could create like 2 copies of you, and it's like, well, that would maybe create a glitch in the matrix. So the universe is like, no, it disallows this kind of glitch by saying there's no cloning, so because of no cloning, this cannot happen.
Yeah, there's something like deeply amazing about quantum, that it's amazing in the sense that like you first learn about it and you're like, oh my god, it has like these crazy powers, and then it turns out to have exactly this like intermediate level of craziness. Like, okay, there's this quantum teleportation, but there's like no cloning, so you can move it, but you can't make multiple copies. Or, with the power of quantum computation, we invented this new model of computation, and we're like, oh, wow, like maybe it'll be nothing. Maybe like we won't be able to solve anything with quantum computers that we couldn't solve classically. Or maybe it'll be totally amazing and we'll solve like NP-complete problems efficiently and so forth. And by some like crazy outcome, like it did this exact thing in the middle where it like, it like didn't do either. It like solved these like, NP intermediate problem. Like, how amazing is that? Or there's like similar things related to like, this thing called like Bell's paradox or Bell's inequality, where, you can use quantum to do something that like seems like faster than light travel, but then it's not actually faster than light travel, but it is still something like amazing that you couldn't do without quantum. So like, it's really wild that like every time, quantum
like
pops up its head.
Spooky action at a distance.
Spooky action at a distance kind of thing. Every time like quantum like pokes up its head, it like, it's neither like unbelievably powerful nor useless. It's like this crazy middle thing. Yeah,
it is interesting. Okay, so one thing I want to get into before we run out of time is actually think about like more interesting generalizations of computation, let's say, or extensions. So we now believe that quantum computers faithfully capture, as we said, the computational capacity of our universe. We have the strong physical church Turing thesis that basically makes that statement that whatever you can efficiently compute within this universe, bounded only by the laws of physics, can be computed efficiently by a quantum computer. And that's great. But it's not like this. I mean, it could turn out that, in the future, we have a better understanding of our universe. We have new laws of physics, and it allows us to do even cooler stuff with computation. So it may not turn out to be a true statement. One like fun thing to think about might be, hey, what if we could travel in time? So while traveling in time, I guess you can go 2 ways. You can go forward or you can go backwards.
Right.
If you're going forwards, well, we know actually that the laws of physics do allow that we can travel forward in time. I can hop on a space ship right now, travel close to the speed of light, come back later, and then, you'll be gone and everyone else will be gone perhaps. From the perspective of Earth, I've, traveled forward in time, and maybe for you, 1,000 years has passed. For me, 1 year passed, perhaps.
Right. So you leave your computer running
on
Earth, and when you get back, you have the answer.
Correct. Yes, that's the idea. Though there is something interesting about that, which is like you try to be clever and like you try to bypass your exponential computation that you needed to do by doing by traveling forward in time, but it seems like the universe will make you pay anyway with exponential amount of energy that you would need to spend.
Yeah.
Right? Because in order to go at that speed, like close to the speed of light, you would have to spend so much energy. To gain that exponential advantage, you would have to spend exponential energy. So the universe is like, no, I'm not allowing you to do this. Like, you have to pay one way or another this cost. But let's think about the other one where we try to travel back in time. Now, that's probably controversial, right? I mean, not everyone believes that maybe that's possible, but it could be possible. And you have actually some work here too. I think
That is true.
I'm very interested in that. So first of all, what would it? First of all, we know about the grandfather paradox, right? So you're like, one thing that people would say, well, we have the grandfather paradox. Like, how can this even make sense to go back in time? And what is the grandfather paradox? Well, if you can go back in time, kill your grandfather before he has his kids, then you'd never get born. And then who's actually doing the killing if you're not born? But interestingly, there seems to be a way to resolve the grandfather paradox and make it logically okay. So what is the way we can resolve this paradox?
Yeah, good question. You know about some of my research. Your grandfather was a professional soccer player, right?
That's right. Yeah.
Pretty cool. Yeah, don't kill that guy.
Played in the Turkish national team.
Amazing. Awesome. Yeah, let's keep him alive. Yeah, so let's see. So there's a story here. Again, I'm shaky on physics, but here's the story as I know it. After Einstein came up with like a general relativity, which is about space and time, that's the extent to which I understand it. There are different possible solutions to his equations, and our old friend Kurt Gödel apparently proved that there existed solutions that sort of allowed for time travel, in the sense that basically it was consistent that you could have a situation where there's like some 2 points in space-time where just by definition, like the state of the particle at this point in space-time is the same as the state of the particle in this time. So it's kind of like a wormhole that like links these 2 points in space-time. And you can mentally think of it as the same point in space, just 2 different points in time.
Right.
So I always like to picture it like, like in your kitchen here, like maybe this wormhole is in your fridge. So it's spatially located in your fridge, but in like 2 different times, like maybe now and sometime soon and sometime in the future. So that's pretty cool. But then, as you say, there's the grandfather paradox, and in particular, Hawking and one other scientist whose name I forget, argued that this is like, although it's like a mathematical solution, it couldn't exist in physical reality because of the grandfather paradox. And you can phrase this a bit more like theoretical computer science-y as follows. You can imagine, imagine you have this like wormhole in your fridge and has space for like 1 bit. And, tomorrow at 9 a.m. in the fridge is like attached to tomorrow at 5 p.m. in the fridge. Like that's the wormhole. It goes from your fridge tomorrow 9 a.m. to tomorrow at 5 p.m. And so like the state of, whatever bit you put into your fridge has to be the same. Okay, and so Hawking was like, I can prove time travel, this is impossible, because one thing you can do is, wake up tomorrow, 9 a.m., you open up the fridge, oh, there's a bit in there. It's either 0 or 1. And then he's like, apply a NOT gate to it. Okay, and then put it back in the fridge. And then at 5 p.m., you have a problem because you say to yourself, oh, suppose the bit at 9 a.m. was a 0. Then I applied a NOT gate, and then it's a 1 at 5 p.m. But that's a contradiction. It's supposed to be the same. And conversely, if it was like a 1 at 9 a.m. and you apply a NOT gate, it's a 0. So then it'll be a 0 at 5 p.m. He's like, contradiction. So this is like the grandfather paradox. But then this other guy, David Deutsch, who is also one of the founders of quantum computation, said, not so fast. There's a solution to this that leaves it as possible. And the solution is, he said, may I remind you that, the laws of nature are quantum mechanical and therefore inherently have some randomization into them. And so you forgot that the state of this bit in the fridge could be probabilistic. And in particular, it could be that when you open the fridge at 9 a.m. and you look at the bit, its state is 50% chance of 0 and 50% chance of 1. And then if you apply a NOT gate to that, well, you get 50% chance of 1 and 50% chance of 0, which is the same. So it's like actually totally logically consistent that, you know, if what your action is on the fridge is to do a NOT gate, there is a allowable state for this bit and everything is consistent.
So the trick is having randomized states.
Yeah, the trick is like admitting that a state can be randomized, or even Deutsch was like, oh, in fact, you know, state can be quantum mechanical,
right?
Which is like an even generalization of randomized. But actually, the observation still works just with randomness.
Yeah.
And so Deutsch had like the same idea, you know, that like Feynman had about quantum computing. He was like, okay, let's hypothesize that there is such a wormhole. What computing power could we get out of it? And it's an interesting problem. You have to like formalize it in a certain way. But then it turns out to be an interesting question. And I got started working on it one time. I was taking a sabbatical in 2014 in Turkey. Mm-hmm. Just a coincidence, but I have a special fondness for Turkey. So I was there for a year. And my host was a theoretical computer scientist there named Jem Sai, who's a great guy, a very interesting guy, lots of interests. And, you know, I got there and I was like, okay, let's find something to work on. And it's kind of like the John story. He's like, okay, here's some things I'm interested in. Quantum is one of them, but I'm also really interested in this like time travel thing. And I was like, it's the same story. I was like, time travel, really? Like, this sounds crazy. But it's like, okay, fine. Like, here we are. Let's work on it. And I worked on it. And actually, I came to like a viewpoint on it, which is like, you can think about the whole problem as not being about time travel, but it's about Markov chains and the complexity of computational complexity of like Markov chains, or in the quantum version, the computational complexity of quantum channels. And so there's like a totally staid, like non-time travel viewpoint on this like time travel problem. So it's like, oh, that's great. It's doubly good. You know, like you can prove some nice facts. And for the skeptics, you can say, oh, we're just talking about Markov chains. And for like, you know, the fun stories, you can be like, actually, we're talking about time travel.
Sure.
And yeah, so we proved some.
So what's like what's like a highlight result there that you can share maybe?
Yeah, I can share one thing, which is this is actually something that was shown before. Maybe it's fully fleshed out by actually Jem and his one of his students. If you have the ability to send one bit back in time, and you don't even use quantumness, you just use, you know, like imagine the world is randomized. If you can send like one bit back in time, then you can solve NP-complete problems efficiently. But you can't solve, you know, everything efficiently. So like, you know, you can't solve problems that take exponential time or things higher in the polynomial hierarchy, whatever that is. But you can solve NP-complete problems efficiently.
Oh. Yeah, that's fascinating. So maybe, I mean, that could be a possibility, right? And then we can augment our Turing machines with a time-traveling bit. And
yeah, Jem has a few more papers about that. Like, what if you have like you can only send them like a short distance back in time or a longer distance back in time? Yeah, interesting stuff.
So I guess we are getting short on time. So let me ask maybe one more question or two more questions.
Okay.
Not related to quantum or computation. It's kind of a personal actually question. So what were some of your biggest failures or struggles in life?
In life?
Yeah. Or in your
academic life?
In professional life, let's say. Yeah, that's better.
Okay. Oh, we have one struggle again with, like, I guess the camera went out. Oh, well.
Yeah, that's my biggest struggle.
Struggle in academic life, keeping the camera on. Yeah.
Yeah.
No worries. Yeah. I can think of a couple. One I can think of is from when I was a graduate student. And I think it's like very, very common for like lots of people. And it happened to me too, which is, you know, I started in graduate school and, you know, you've started at the same time as a lot other, you know, people your age, and you're all trying to work on research. And, you know, I got the feeling, and it's not just a feeling, it was true, that like, you know, lots of my contemporaries, you know, were very successful early. You know, they, you know, published papers in their first year, and they had like a research program going like after like seemingly a short amount of time. And I felt like really bad because like I was at graduate school for 1.5 years. And graduate school normally takes 4 or 5 years. And like I hadn't, published any papers. I hadn't solved any problems. And, I felt like, envious and like, can I do it? Like, what's going on here?
Right.
And yeah, that was pretty tough. I remember feeling kind of down then. And yeah, I mean, I actually, I decided that, you can't, you just try not to compare yourself to other people. I mean, everybody's, different. And yeah, just try to be the best you. And, it'd be great to say, and then, I like, finally I solved that first problem and like, then I was ready to go. But actually it was not like that at all. For my first paper, like I was trying to solve some problem and it wasn't really getting along. And I went into the office of like a new professor at the graduate school, Piotr Indyk. And I had some like technical question for him. I was like, do you know about this thing? You had a paper about the randomization, blah, blah, blah. Can you do this technical thing? And he gave me some answer. And then he's like, oh, your question kind of reminds me of something. And he started like kind of scribbling at the board. And he's like, oh yeah, I think this actually solves some problem I was working on. And he's like, okay, you're on the paper. And I was like, I didn't even do anything. Like I literally didn't do anything. I didn't even know what the problem he was trying to solve. But he was like super generous to me to like, like get me involved with this project, even though like I literally contributed nothing. So, I mean, I tried to understand this. So even like, my first like success in terms of like publishing, I was like, oh, thanks, Piotr. Like I didn't even do anything. So that was one such struggle. I can even remember another one from my, when I was an undergraduate. Like when I was an undergraduate, I studied math and computer science, as you might expect. And in my first year, it was, I don't know, I found everything came quite easily to me. Like I understood all the math topics and the computer science topics and, it was fine. I got like straight A's, not to brag, but that was great. And then, okay, like second year came along, sophomore, and I remember I took this one, like, the calculus course, like calculus, second year calculus on manifolds. And had this really short textbook by Spivak. And like, I didn't get it. Like I couldn't understand it. I couldn't follow the theorems. I didn't understand the motivation. I had a hard time solving the problems. And I acted in a really bad way. Like I actually kind of, I thought it was the professor's fault. I thought, like she's not explaining it very well. If she just explained it properly, like we'd understand it. And, I was like, I don't know, kind of rude. I think I like went to our office hours and said something that was like, I can't, you're not explaining things right. This is like, why don't I get it? I mean, of course I didn't get it because like, I wasn't like, I wasn't studying in the right way. Like I just kind of assumed it would be easy. And if I just like looked at it for like a short amount of time, I would get it. And it's not like that in math. Like, I mean, you really need to like buckle down sometimes and spend like a lot of hours thinking about something quite simple. And I didn't do that. And so, yeah, at first I blamed other people. So sorry about that. Echo Hironaka, if you're out there, you were right. I'm sure you explained it great. And I hopefully learned how to, study better.
Yeah, that's awesome. Well, thanks a lot, Ryan. This was a lot of fun.
Yeah, thanks for having me.
I hope we can do it again sometime because, I learned a lot. Definitely enjoyed this a lot.
Yeah, it was great chatting with you.
All right. Thanks a lot. Thanks, everyone, for joining in. See you guys soon.
All right. You want to get in the shot and like wave at them? Or?
Well, yeah. Yeah, I can do that.
All right.